Hey, what's up, guys? So in this video, I want to prove that one important formula in the Fourier analysis, Fourier transform and the inverse Fourier transform. Okay. So this formula is the following that you might see like everywhere that 2 pi delta omega satisfy this. Okay, so this is the formula that plays an important role in the like Fourier transform, right? So given f, which is from like say a real number to real number, that one can define a so-called Fourier transform by just so-called change it to the frequency domain. Sometimes it's plus I omega t for sec change dt, and one can define a so-called inverse Fourier transform. So we'll go, this is just take this original f hat of omega and times minus this, and go back to the original function. So this is f of t. Okay, so if you just try to write down all this proof, then you will find that you will need this formula. Okay, so this formula actually plays an important role. Actually, if you know this formula, this is also called orthogonality relation in like finite group representation. Then this will give you all kind of Fourier transform. All kind of actually in all the different kind of Fourier transformation, like either finite group that or like in like for a series that there are always one formula which you can do some kind of like this to make sure that the transform and inverse transform give you the exact one. Okay, so this is somehow like a mysterious formula. Right? If you like just look at the left hand side, right hand side, you will find that somehow like hard to prove, right? You will know, oh, so why the first transformation of one function, like identity function, give you the delta? I mean, it has some physical meaning, but somehow like hard to explain by this. So just try to somehow like it's hard to just give you the proof. Okay, so this is why I want to like go through the proof. So to understand this kind of equation, that you should notice that the left hand side is not a function, right? It's basically delta function. So all you need to do is that prove that this the right hand side takes some limits, give you the left hand side, and give left hand side as a property, which you need to show. So basically the goal is to show if I take this guy, maybe I take some finite cutoff, let's say delta, okay, and I take limit delta goes to infinity, and I will assume that this is this guy, okay, and this guy is basically the delta function, right? So you should have any kind of property that delta function have. Actually by definition the most important one is the integral one. Okay, so you should times g of omega d omega from infinity to negative infinity to infinity. This gives you g of 0, right? So because this is looks at the property of 2 pi delta omega, so you get this 2 pi. Okay, so the goal is that if you can prove this formula for any like well-behaved function g, then somehow that you prove that this serves as delta omega. Okay, and in general, you need to prove the shift one. So you need to actually prove the following with the shift one. But this is simple and trivial that you just do the change of variable that you can show that proving the above one is the same as proving the lower one. Okay, so we just need to prove this guy, and then it's indeed just prove this guy. Okay, yeah, let's write down a proof. Sorry about this one. Okay, so let's write down a proof. Okay, one page should be enough to prove this simple result. Okay, so from this delta to delta, that we know that we need to compute this, right? Okay, so this is simple. That basically is 2 I omega exponential I omega t, and you just plug delta and negative delta, that you get exponential I omega delta minus exponential negative I omega delta divided by 2 I omega, and this by definition is sine, right? So sorry, there's no 2 here. So you get I omega and 2I sine omega delta. So I will just, so I cancel, so you get actually 2 sine omega delta divided by omega. Okay, so we need to take the infinite limit, right? So let's say the infinite limit to sine omega delta divided by omega for any g of omega will behave, and do the d omega integral from negative infinity to infinity. Okay, so we are not doing like mathematical analysis, right? So we cheat a little bit. We just exchange the integral and the limit. Okay, this is actually not a non-trivial step here. Okay, so we get to sine omega delta divided by omega g omega d omega. Okay, so the difficult part in this proof is that you need to integrate d omega, right? But actually you have no way to do this because this is not doable in general. There's no analytic formula. Okay, but one way is that you take some limit, right? So you should you just change do some change your variable. Okay, so this is the trick. The trick is that there's a epsilon is 1 over delta. So we get limit of epsilon goes to 0 and infinity. This integration and the 2 sine of omega divided by epsilon and omega divided by epsilon and d omega divided by epsilon. So I just do some exchange and the g of omega divided by epsilon. Okay, so this is just sorry, let me just see. So yeah, so I just write delta to be omega divided by epsilon, right? So this is still g omega. Sorry. Okay, so now I can do the change of variable. I can do a change of variable again, right? Just say so I can write omega divided by epsilon to be omega delta. Okay, just for the for the convenience. So let's write limit epsilon divide goes to 0, that you get negative infinity to infinite. So to sine of omega delta d omega delta and the g of omega divided by epsilon. Oh, sorry, I write again, right? So this is, yeah, so the following. So we just, yeah, so this is just epsilon omega delta. Okay, so what we have is the following. So infinity to negative infinity to infinity to sine omega delta d omega delta and g of epsilon omega delta, right? Inside this integral, because I change omega to epsilon times omega delta. Okay, so we have this. Okay, so now notice that when you take a limit of epsilon goes to 0, there's only one dependence here, right? So you just take out this and you write as g of, but epsilon goes to 0, right? So it's g of 0, and then all you need to compute is the following integration. Okay, and amazingly that this integral is computable, right? You can use in your complex analysis. So actually this integral is pi over 2 with 0 to infinity, so it actually is twice, right? So the important formula is the following. This one, 0 to infinity sine x divided by x dx is pi over 2. Okay, so you can prove this using the complex integration. So if you don't know how to prove that, you can check out my other videos. But actually, this is you can easily find the proof online. Okay, but you change from infinity to infinity, right? So this integral need to be times 2, so it's like pi, right? So you get 2 pi g of 0. Okay, so 2 pi g of 0 is exactly what we are gonna do proof, right? So that means that these guys serve as 2 pi delta omega. So that 2 pi delta omega g of omega integral with this omega will give you the 2 pi g of 0. Okay, so this indicate that this function actually serves as 2 pi delta omega. Okay, so this is the proof. Okay, so see you guys next videos. Hopefully this video will help you to solve some confusion.